way. So key things, key features of the normal distribution. So it's a probability distribution model for continuous random variables. It's pretty perfect in the shape that it is. And there's some really key properties to look out for. So it's a kind of bell-shaped curve. So it's this kind of perfect picture here, bell-shaped curve. And it's a continuous random variable that can actually take one of an infinite amount of values. So it's a kind of strange concept. So it's a continuous one, which is very different to the discrete binomial we just saw. Now, the normal distribution is a probability density function that models actually naturally occur in situations, heights, weights, for animals, for plants, for anything, things that have this sort of distribution where the mean, the median, the mode are all the same. They're all in the middle. And there's a natural kind of variation above and below. Few other properties to just pay attention to. So the way we denote this distribution for a start is we would say X follows the normal, and the population parameters we care about are mu and sigma squared. So already looks very different to the binomial. Key thing to also add is mu, which is our population mean, is actually equal to the median and the mode. That's a fact you would be expected to just know for this distribution. And sigma is talking about the standard deviation. So loosely speaking, that's the average distance of anything from the mean. So just a quick point on notation. Mu represents the population mean. X with a little bar above it represents a sample mean. So don't confuse those. Other key properties of the normal distribution. Oh, typed in for me. There we go. Is it's symmetric, perfectly symmetric. Points of inflection at mu plus or minus 1 standard deviation. So this is our link to pure maths. We mentioned points of inflection before. Points of inflection are where a function changes from concave to convex. So it actually like changes shape. And they perfectly exist 1 standard deviation away from the mean. And the other key thing to consider is the total area under the curve is 1. Now, thankfully, you don't have to do this at A level. I don't even remember doing this at university, but that would mean technically that if you integrated it, the area under it would be 1. Thankfully, we don't have to integrate the normal distribution curve, but that's something we need to consider. Okay, so this value here, let me just annotate that on, is mu minus sigma, and this is mu plus sigma, and this is mu. Okay, few other key points. Now, this is generally for a lot of the exam boards, your textbooks and stuff will write this in. There are some key amounts to know. So generally speaking, 68% of the data, it's worth knowing this kind of by heart, lies within 1 standard deviation of the mean, basically there. Please do send any questions in. As we said, we've got the live messages to the tutors and by email as well, because I understand that this is quite full on at this point. Now, 1 standard deviation of the mean includes above and below. 68% of the values will lie there. Within 2 standard deviations of the mean, that will incorporate 95% of the values. And then three standard deviations above and below the mean is almost like 99.8% or something. So when you're picking a value to choose that covers everything, if you go 5 standard deviations above or below the mean, that will pretty much cover everything for the level of your calculators. So that's worth knowing. You can be expected to know those kind of figures. And so we're going to see that in a kind of question now. So this is a really good one, actually, because it matches the graphs to the shapes. So let's explore this now. So on the next page in your booklet, you're going to see 4 graphs, the X value of their turning points, points of inflection, and also we need to look and reason why, which one isn't a normal distribution, which one is a normal distribution with the lowest variance, and which one has an area between minus 1.6 and 3.6 equal to 0.95. So have a little look at the graphs now. I'll put them up. These graphs. Hopefully you can see them in your booklet. Now, referring back to the question, we need to pick out the 3 that represent that information there. Some of this is quick. You can do this by elimination, process of elimination. I'm going to give you 1 minute to have a little think about that, and then I'll guide us through. But give it a try. Quite a nice question, hopefully. Right, I'm just going to carry on, guys. So let's have a little look at these. I do want to clarify a few things about what values you input in your calculator as the upper bounds and stuff. But I'll do that as we approach the hypothesis testing, because at first we want to just get familiar with how these look. So to start with, if we look at each of these, I'm hoping that one of them really stands out to everyone as clearly not perfectly symmetrical. So the one that's not, that's right. So the one that's not a normal distribution, hopefully we're going to identify is the one at C. So straight away, it's not symmetric. So the kind of, you can also see from the points of inflection, they're not equally far apart. So that one straight away is not a normal distribution. So now we've got the other graphs. For part 2, we want the one with the lowest variance. So this means that the spread, if the variance is low, then it would also have the lowest standard deviation, meaning that things aren't spread that far from the mean. So this is the one with the kind of sharpest peak, the one where everything is more compact and spread closer to the mean. So this will be graph D. Now this bit, interpret this one. If this is 95%, remember this means it's within 2 standard deviations of the mean. So looking at that information, we can actually work out that that would have to have a mean of 1 and a standard deviation of 1.3. So the only one that matches that is this graph here. Now we'd already narrowed it down to A and B. But what we were saying, just to revisit that, because I know that was quite quick, is that it was using that fact we mentioned earlier, that 95% of the stuff lies within 2 standard deviations of the mean. So we know the region we're looking at. And so this and this must represent mu plus or mu minus 2 standard deviations. So we can form simultaneous equations to find out what mu would be and what sigma would be. So this was again a matchup and a process of elimination. And we can see that that would be graph B.